Hello, everyone, and welcome to our happy dive into modern data analysis for physicists. I am your host, and today we will explore the big picture of machine learning, how it empowers data-driven knowledge discovery in physics. Every physics question, whether it's mapping electron orbits or tracing cosmic rays, boils down to one thing: algorithms. For decades, we hard-coded those algorithms ourselves: clear, static, deterministic, named rule-based system as shown in the first line. However, think of all the terabytes pouring out of modern detectors. Classical, handwritten code struggles to squeeze meaning from that data avalanche. Today we have a new ally: machines that learn. In simple words, machine learning is the art of letting computers improve their own algorithms instead of having us write every single instruction. The second line thus shows a machine-based mapping of a data stream to the desired result. Here we selected the most promising variables, and the machine automatically learned the required algorithm from training data. And why do we care? Because it opens the door to data-driven knowledge discovery, turning raw measurements directly into fresh scientific insight. As line 3, we do not select the most relevant variables to solve the challenge by our physicists' knowledge, but leave it to a machine. This is called representation learning. Finally, line 4 in the figure, the milestone is deep learning. Deep learning stacks many processing stages, extracting ever richer patterns from the inputs. Deep learning lets the data sculpt its own algorithms, and in many cases, it outperforms our best handwritten code. Here arrives a branching flowchart, the so-called decision tree, making yes or no splits until each object lands in either the signal bucket or the background bucket. A decision tree is a classic example of a machine-based optimization. Physicists still handpick the observables, maybe energy and momentum. The tree simply learns the best order and the best cut values. It maps a handful of chosen inputs to a target answer. Yet mapping has limits. When you input raw images, waveforms, or millions of pixel intensities at a decision tree, it throws up its metaphorical branches in despair. Now you see a neat little neural network sketch: 3 inputs, x1, x2, and x3, 2 hidden layers of 3 nodes each in the middle, and 1 output, z. All network parameters have already been adjusted here. Every blue line represents a weight that multiplies an input or an earlier node's output, respectively. Each circle is a node, works on its input, and ships the result forward. Layer after layer, the network invents brand new composite observables. The color intensities of the connections and nodes symbolically show the paths through the network in response to the 3 input values x1, x2, and x3. We refer to the output value z as the network prediction for these input values. Side by side, you see 2 cartoons. On the left, a rule-based flowchart. On the right, a densely connected network, our connectionist system. Time for an important contrast. Rule-based systems follow explicit, human-written if-then rules, one after another. Connectionist systems like neural networks spread the intelligence across the structure itself. No single node knows the global task, yet together they nail it. That shift is monumental for physicists tackling complex datasets. Let us briefly address uncertainties, because physics never stops caring about error bars. Statistical uncertainties stem from counting, think Poisson fluctuations, which will be directly reflected in the output z. Systematic uncertainties arise from calibration shifts or model mismatches. Change a calibration constant and the entire input vector x wiggles. The network dutifully propagates that change to the output z, letting us quantify the induced variation. What fueled the rapid rise of deep learning? 4 drivers. First, innovative architectural concepts, convolutional layers for images, recurrent gates for sequences, or transformers suited for various tasks. Second, GPU acceleration, which crunches matrix multiplications hundreds of times faster than a traditional CPU. Third, giant training datasets, millions of labeled images, hours of speech, or in our case, petabytes of simulated events. Fourth, open source software libraries such as TensorFlow and PyTorch, letting any motivated physicist design sophisticated networks with just a few lines of code. The final diagram shows concentric circles, artificial intelligence outside with machine learning, representation learning, and deep learning nested inside. This hierarchy reminds us that deep learning is one part of the broader artificial intelligence family. Crucially, human expertise remains inside the system. We physicists select meaningful goals, design network architectures, and review the results. The computer supplies the horsepower, we supply the insight. And there we have it, our joyful tour from machine learning fundamentals all the way up to the frontiers of artificial intelligence. If you enjoyed the ride, follow our textbook, grab the companion notebook, load your favorite dataset, and let those networks start discovering. Thanks for watching, and stay curious.